On to lesson 6, which focuses on algebraic expressions. Algebraic expressions depict mathematical relationships using a combination of numbers, symbols, and variables. Variables are essentially letters that replace unknown numbers in an equation, a function, or a numerical expression. Algebraic expressions denote numerical relationships by using a combination of variables, numbers, and mathematical operations. Variables are symbolic representations of unknown quantities or quantities that vary. Variables can be represented using letters, for example, x or y. Each time the same variable representation is present within an expression, the variable represents the same quantity. So for example, if you were given an expression 3xy plus 8x plus 9z, and you're told that x is equal to 2, then in your original expression, everywhere where you see x, just know that it can be replaced with the same quantity, which in this case would be 2. To solve algebraic expressions, change numerical relationships described in words to their algebraic equivalents. So here are a few examples of algebraic expressions translated into their symbolic representations. The product of 5 and a number can be rewritten as 5 times x. Why? Well, we don't have any information about what the unknown number is. It could be 100, it could be 45, negative 75, or even 0. In other words, it can vary, and as a result, we have leeway to represent this unknown quantity as a symbol. In this case, the author has chosen x, so the product of 5 and a number can be rewritten in symbolic form as simply 5x. A number decreased by 12 can be rewritten as x minus 12. Again, the idea is that we have no information about the number, we just know that it decreases by 12. So we can represent the unknown number or the unknown quantity as x and restate the expression as x minus 12. So note that x can take on any singular value. So let's say that we have predetermined that x equals 100. In this case, 100 minus 12 would give us 88. Or x could represent a term. So for example, we could have 100 minus 20 divided by 5, and the entire term, 100 minus 20 divided by 5, could be represented by x, knowing that no matter what is on the left side of operation here, which in this case is subtraction, so no matter if it's a single value like 100, or if it's a more complex term like 100 minus 20 divided by 5, we know that that value or that term will always decrease by 12. Or we can just simply rewrite the expression as x minus 12. The sum of 3 and the square of a number can be written as 3 plus x squared. 6 less than the quotient of a number and 2. So let's think through this carefully. You remember from our earlier lessons on division, we know that a quotient is the resultant number from a division operation, right? So here we're told that the quotient comes from a number. What number? We don't know. It's a variable, so we can represent it with x. So the quotient comes from some unknown number and 2. So this can be rewritten as x over 2 or x divided by 2. We're also informed that the quotient is 6 less. In other words, 6 is being subtracted from the quotient, and the quotient is derived by dividing some unknown quantity by 2. So we can rewrite this expression simply as x over 2 minus 6. 1/2 of a number increased by 15. Again, just thinking through the information that we're given here. 1/2 of a number, what number we don't know, so we can just represent that unknown number or quantity simply as x. We're also told that this unknown number, once it's been halved or divided by 2, then increases by 15. So symbolically, we can represent that as 1/2 times x, or half of x, or simply x over 2, plus 15. 4 times the difference of -3 and a number. So whatever this unknown number is, we know that it's being subtracted from -3. And that difference, remember, a difference is the outcome of subtraction. Here, the difference of a -3 and a number simply means that when you subtract -3 from an unknown number, let's call it x, what you get from that operation, or the outcome of that operation, is the difference. And that difference is being multiplied by 4. So you want to make sure that you're capturing the expression that represents the subtraction operation that yields your difference by putting -3 minus x in parentheses. And we also know from the statement that the difference term here is being multiplied by 4. So we can rewrite this entire expression as 4, open parentheses, -3 minus x, close parentheses. A number less another number. So here we're dealing with two unknowns being subtracted from each other. We can represent the first unknown as x and let the second unknown be y. And so this algebraically can be rewritten as x minus y. So in this next example, we're given information about 10 less than the square root of the sum of a number and 3. So if you want to start by isolating the number or variable, and then also the operation that's mentioned first. So two things you want to isolate, either the number or the variable and the corresponding operation. So here, 10 is the first number mentioned. Less, indicating subtraction, is the first operation mentioned. So we know that we are subtracting 10 from the square root of the sum of a number and 3. What is the number? We don't know, but we can represent it symbolically as x. We do know, however, that this unknown number needs to be added to 3, after which point we need to then take its square root and subtract the result from 10. So we rewrite this symbolically as 10 minus the square root of x plus 3. So in this particular example, we're being asked to subtract 3x squared plus x plus 4 from 7x squared plus 2x minus 16.